Hello scholars, Ms. Beglin here with your Unit 1, Lesson 4, Measuring Ionization Energy, Photoelectron Spectra, Independent Work. Firstly, I want to continue to apologize profusely for not getting this to you earlier. I hope that the extended deadline makes it up, and I am taking steps so that this does not happen again. Scholars, this is going to be a longer video. I'm going to give you cues to take breaks between different segments. I highly recommend that you take those breaks. With that being said, let's move forward. Yesterday, we answered the question of how do we make ions, but we still have to answer the question, how do we measure ionization energy? The process for measuring ionization energy is very similar to the process for making an ion. We hit an atom with light or electromagnetic radiation that has sufficient energy to overcome the force of attraction between the electron and the nucleus, ejecting the electron from the atom. The key difference is that now we're going to measure the exit velocity of that electron that was ejected so that we can calculate its energy. And we would just calculate its kinetic energy. So we can calculate the energy of our ejected electron. And we also know the energy that we put in because we can calculate the energy of electromagnetic radiation. According to the law of conservation of energy, my energy in should be equivalent to my energy out. However, what we see is that the energy that we put in is much greater than the energy that we get out. So at some point in our process, we lost energy. We violated the laws of nature. But the world hasn't exploded, so there must be an explanation. The missing energy was used to overcome the attractive force between the electron and the nucleus. We call this the binding energy, or the energy that binds the electron to the nucleus. So our energy that we put in was used to eject an electron at a certain velocity, but before it could do that, it had to overcome the binding energy. Scholars, you may be thinking, wait, we were talking about binding energy. How did we get to ionization? We were talking about ionization energy. How did we get to binding energy? The answer is that these things are related. They're not exactly the same though. Binding energy measures the attractive force between an electron and the nucleus, whereas ionization energy is the minimum energy needed to remove a valence electron. As we can see, they're not equivalent, but they're pretty much the same. So a lot of people use them interchangeably. And they are related. As binding energy increases, ionization energy will also increase. And that just kind of makes sense, right? If the binding energy is higher, the electron's being held more tightly to the nucleus, of course I'm going to need more energy to remove it. So you may hear these terms used interchangeably. It's not totally wrong, but I just want you to be aware of it. One key difference is that binding energy is the same for all electrons in an orbital. So these two electrons in the first orbital here will have the same binding energy. These 8 electrons in the second orbital will have the same binding energy. Whereas we know that successive ionization energies increase due to the changes in ionic size that impact the force of attraction. This process of bombarding an atom with light to eject an electron and then measuring the exit velocity so that we can calculate the binding energy is called photoelectron spectroscopy. For the word spectroscopy, think of that as meaning a means of measuring. Here we have photo from our light, our photon, and electron. So this literally just means measuring with light and electrons. And the thing that we get from it is a photoelectron spectra. Now, we're going to do some practice with reading photoelectron spectra. This is a really good time to take a break if you need one. Welcome back. So now we're going to dive into examining photoelectron spectra. We're going to start with the simplest element, hydrogen. 1 proton and 1 electron. Here's the photoelectron spectra for hydrogen. Now let's take a look at our axes. Our x-axis is our number of electrons. Our y-axis is our binding energy. So we see that we have 1 electron that has a binding energy of 1.31 megajoules per mole. Being able to read the numbers is not important. The key thing you have to notice though is that the x-axis is number 1 on a logarithmic scale, and number 2, it decreases. Going across. I have no idea why it decreases going across. I don't know who made that decision. Now, a lot of times we want to represent where electrons live in an atom so we want to represent where electrons live in an atom. And we do this using something called an electron configuration. So let's write the electron configuration for hydrogen. We start with a number. This number indicates our energy level. So we're in the first energy level, so our number is 1. Then we have a letter, which basically indicates the shape of the orbital. This is a sphere, so we call it S. And then we have a little subscript up here to indicate the number of electrons that live right here. So we have 1 electron living in the 1s space. Let's take a look at helium. Make a prediction. How do you think the photoelectron spectra for helium will be different from the photoelectron spectra for hydrogen? I am going to predict that it'll have the same binding energy because they're both in the 1s orbital. And our height will just be 2 times greater to indicate that I have 2 electrons. Let's see what happens. Okay, I have my 2 electrons, great, but what's this? My binding energy for helium is higher than my binding energy for hydrogen. Why do you think that is? All right, let's say we made a mistake. Let's look at our photoelectron spectra for lithium and beryllium. Let's start with lithium. I have 2 electrons that have a very high binding energy. My highest binding energy will always be my 1s because that's the closest shell. And then I have 2 electrons. Now I have 1 electron over here, and it lives in the second shell. So we'll call that 2s1. So my electron configuration for lithium is 1s2, 2s1. Let's do the same thing for beryllium. I always start with my 1s, and I see that there are 2 electrons. And now I've moved to occupying my 2s, and there are also 2 electrons. And the shift happened again. Beryllium has a stronger binding energy than lithium. Why is that? Well, what do we know as we move across the periodic table? Yes, we know that ionization energy increases, but why? Because atomic radius decreases. For elements in the same period, changes in bonding energy are caused by changes in atomic radius. Scholars, this is a good place to stop if you need a break. All right, I think I've got the hang of this electron configuration thing. I'm going to write the electron configuration before I even see the photoelectrons. I have my first shell, 1s, and I have 2 electrons in it. And then I have my second shell, 2s, with 3 electrons in it. I got this. Okay, here's my 1s with the 2 electrons. Here's my 2s with 2 electrons. And what the heck is this? I should have, like we said earlier, 2s3, not 1s2, 2s2, whatever this thing is. What the heck? Why is this 1 electron not over here? Scholars, the model of the atom that you are used to seeing is commonly referred to as the Bohr model of the atom. It was photoelectron spectra just like this one that led us to say, this might not be so accurate. It was retired in favor of atomic orbital theory. So an atomic orbital is a region that an electron is likely to occupy. Kind of like how we're used to thinking of shells. Each orbital holds 2 electrons. Then we have subshells. That indicates the type or the shape of the orbital. And finally, we have our shells, which are our energy level. So even though the Bohr model of the atom was retired, it's still a really useful conceptual model, and it's how we developed atomic orbital theory. But when confronted with data that didn't match it, we had to refine it. So we have our 1s2 orbital, or we have our 1s orbital that holds a maximum of 2 electrons. Our 2s orbital that holds a maximum of 2 electrons. And then we have 3 what are called p orbitals. And because they're in the second energy level, it's 2p. P orbitals have this kind of dumbbell looking shape. So in this shell, this gives us a total of 4 orbitals, which each hold 2 electrons. So 2 times 4 is 8. This is the atomic origin of the octet rule. So let's revise our electron configuration for boron. I still have my 1s2. Now I'm going to say it's 2s2 followed by 2p1. And the superscripts add up to my total number of electrons. So I know I'm doing something right. Scholars, the really cool thing about this is that you don't have to memorize it. It's something that lives in the periodic table of elements. So we call this section the S block. And we call this section the P block. And we can literally move through the periodic table to write the electron configuration for anything. Let's do some examples. Write the electron configuration for nitrogen. Okay. I'm going to start at the beginning of the periodic table. I move through the first row. 1s2. Then I'm going to move through the second row. I've moved entirely through the S block, so I'm going to say 2s2. 1, 2. Here I hit the P block. So 2p, 1, 2, 3. That's it. You can also write the electron configurations for cations and anions. Let's do that. We'll start with the sodium ion. And whenever you're writing an electron configuration for a cation or an anion, you want to start with the atom. So let me find sodium on the periodic table. Let me change the color. Right here. I start at the top. 1s2. Green was not a good decision. Purple will be better. 2s2. 2p. 1, 2, 3, 4, 5, 6. And now we're at 3s1. Okay, that's for sodium. I was asked for the sodium ion. When we remove electrons, we remove them from the valence shell. So I'm going to just cross this out. 1s2, 2s2, 2p6. And we can see my valence shell has 8 electrons in it. Let's do chlorine. Chlorine's over here. Move through the periodic table, starting with, oh, sorry, that's Cl minus. So let's start with chlorine, move through the periodic table, 1s2, 2s2, 2p6, 3s2, 3p5. Chlorine minus. When we gain electrons, we add them to the valence shell. So everything stays the same. This one is full. So I'll add 3p5, 3p6. Okay. Scholars, this is a good time to take a break. You may be wondering, what about the transition metals? Nobody ever asks about the lanthanides and actinides. Nobody cares about them. But we do care about the transition metals. The transition metals are commonly referred to as our D block. So we have 5 d orbitals. Their shapes are like this. They, for the most part, look like 4-leaf clovers, except I don't know what's going on with this one. Had to be different. Each one holds 2 electrons. 5 times 2 is 10. Scholars, that's exactly how many rows there are in the transition metals. They start one level below. So here's 4s. Scandinavium starts at 3D. All transition metals technically have 2 valence electrons because they start one below. It validates the octet rule because all of these extra electrons don't interfere with our 4s and our 4p. That can hold 2 and 6 for a total of 8. The energy levels of the 4s and 3d orbitals are very close, which is why transition metals have weird charges. Let's do some examples. Write the electron configuration for molybdenum. All right, let's go. I'm gonna find molybdenum. She's over here. Scholars, that's so far down the periodic table. I don't want to write all of that. Thankfully, I don't have to. The full electron configurations are the ones we've been doing. We can also write noble gas configurations. So we cheat. We start at the previous noble gas and we put it in brackets. And then we just keep going. So we say this one would have 5s2, 4d4. So much easier than writing out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. (3d10), 4p6, and that, so all of this, that just got us to krypton. And it's contained in that little bracket. And then we get to our unique stuff. Bromine. Bromine's not that far down, I'll write it out. So I have my 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Scholars, if you were like, you know what, I'm not going to do this, Ms. Beglin can have fun. The noble gas configuration for this element for bromine is argon, because that's the one before. 4s2, 3d10, 4p5. All right. Let's do a cation, specifically a transition metal cation. We always start by writing our atom. So here's zinc. I'm not writing this stuff out. Argon is the nearest, or the previous noble gas. And then we have 4s2, 3d10. We have to take away 2 electrons. We always take them from the outermost shell. So we get that Zn2 plus has the electron configuration of argon, 3d10. Scholars, that's it. I know it was a lot. I believe in you. Thank you so much. Please email me with any questions. Love you guys. Bye.